Basically, the most obvious thing to do with the language model is being done.
Well, super compilation has been invented 20, 30 years ago, when one language is compiled in an optimal version of even the same language, linguistically,
Okay.
without actual compilation, and then only the real compiler. So let's see, this is like a super compiler.
So, okay, I'll start. So, hello everybody. I'll be presenting the paper evaluating large language models, which is trained on code, on all the code. So this this paper basically, it only considers Python into for all the evaluation and generation part. And so we'll be talking about the sequence modeling, the data collection of, and how did they fine tune the data, and also a very interesting evaluation metrics, which is like the human evaluation which they did, and also a pass act K metric which they took for by using the human evaluation. Then I'll also be talking about the work which we like a group of guys like we did on like to replicate the same thing for competition, and also the future work implementation of this. Okay, so this paper basically it talks about so this, before even going to the paper, it only talks about the GPT-3 model. So GPT-3 model was basically a model which was trained on a large text data set, which included all the Wikipedia and every text possible which is in internet as what they told us. And then so what they tried is that they tried to generate doc strings out of those out of the GPT-3 model, and then they got an idea like, why don't we do it just for the code? And so that's where the idea came from. And they told that the GPT model, this one is, the paper is about I mean, so they have actually trained like 300 million parameters, out of 12 billion parameters, and out of that they have only taken like GitHub repositories, which is like publicly available code. And so that's the problem. Like, there's few problem which occurs if you're taking code from a public repository from GitHub. And so they took like around 179 GB of GitHub data, but after fine tuning it, it's like they're fine tuning it to 159 GB. And I'll tell you like how much 159 GB of GitHub data is exactly. Then they do talk about the human eval data set, which basically measures the correctness of the program, which is generated from the docstring and the function header. A good thing about this human eval data set is that the people in OpenAI, they hand wrote it, and then like this was all very custom made. They didn't take it from somewhere else. They made the whole data set just for the evaluation. And apps data set is basically it was already there. The apps data set basically contains all the competition like, so for example, Kickstart and LeetCode and Beats for Geeks. So all the competitions and this coding programming environment, and they took all the all the problems and the solution, and they made a data set out of that. So they're taking these two data sets and then they're evaluating on that. So when they try to do it in GPT-3, which is like the base model, it actually solved nothing. So that's the 0%, as you can see here. And then they used a better GPT model, which was by Ulithium AI, and that went to 11.4. And the Codex, which we are going to talk about now, is going to solve like only 28.8% of the whole thing. So whatever you're seeing in Codex or even in GitHub Copilot, that's only like 28.8% of whatever they have done. So this is what generally it looks like. So if you define a function like here, increment list, and you give a list, and then the main thing that you have to see here, that you have to give a very defined docstring here, like return the list with elements incremented by 1, and then this is what the result will be generated. So like similarly for this, like encode cyclic and all that, but so the main thing is that you have to give a very defined docstring. The problem with this is which we'll also discuss later, is that if you give a very complex docstring or if a very long docstring, then it will not perform really well, and that's an issue which I'll be discussing later on. So here, most of the code most of the fine tuning that they have done is basically on the GPT-3 language model itself. So basically, for those who are not very familiar with sequence modeling, it's like I've given an example here. I'm going for a walk outside to get some. So there's a mask which will tell me what is the predicted output of that sentence, of that word. So they are using couple of methods here. Like for example, they are using repeated sampling, which is like the main part, which they told in the paper also, that's the main part which they're doing. So what repeated sampling is going to do is that it's going to take like all the prediction from all the sentences, and it's going to give us a cumulated prediction of that sequence, and then it's going to replace it with the mask. So it's not going to go word by word. Instead, it's going to go sequence by sequence. So that's where it's actually working on. So when you're working on code, also you can't go like if I'm going to write a code like for I in range, that's okay. But what if I'm writing a very complicated code, which like let's say torch.grad.autograd, like about what comes after that. So that's where it comes handy. And so talking about the data set here, as I told before, they're taking all the publicly available GitHub data, and they're also taking the pile data set, which is also publicly available. But what this pile data set contains is that it contains all the Python code along with Stack Overflow problems. So what this solves is that you'll have all the code, plus you'll have a lot of description on the code also. So that's why they're taking Stack Overflow problems, because they have the description of the problems, and then again the solution which is there in the Stack Overflow. So they also mentioned that there are more than 10 public repositories which contains the solution for code forces problem, which makes up for the recently proposed apps dataset. And that's what I said before also. So all the code forces or Geeks for Geeks or Kickstarts and all those problems, they have taken it and they have put it in one apps dataset. So the advantage of having this apps dataset is that you have a very defined problem statement. Like you will know like what needs to be done and how you want the code to be generated. So that's what they're taking. But the difference between the apps dataset and the GitHub or the pile dataset is that the apps dataset, they want you to also have the input and output code. So you have to code the input and output as well. So that's where it differs from other dataset. So as I was saying, since Codex is evaluated on natural language prompts, they hypothesized that it would be beneficial to fine tune on the GPT-3, as I told before. But surprisingly, they did not observe a very good, improvement when starting from pre-training the language model, because the thing is that when you're talking about a language model, or even if you want to train it, there are a lot of white spaces which are included in natural text. And but in the code, the white spaces concept is a whole lot different, because you might go to another line, you might have different brackets which will open and all that. So for that, they used a different kind of tokens, like they use additional special tokens for representing white spaces, which basically reduce this problem by 30%. And also this reduced the data set by 30% as well. So that's a very interesting thing which they do. But going forward also, I think, so along with this they also took a parameter called temperature, which I'll talk in the coming one. So this is where, this is the data set which they collected. So they collected like 54 million public repositories, and that's a lot, which contains like 179 GB of unique Python files under 1 MB. And so they took some criteria, like filtering criteria for taking the GitHub repository. So they took like average line length, which is like 100, average line length, they didn't mention. The maximum line length is going to be 100, and small number of alphanumeric characters, which is going to be 1000. That's the filtering criteria which they took. And after filtering, they came up to like 159 GB of Python files. So for an example, like big 159 GB of code is. Like if I take this Keras code time series classification with a transformer model, that's basically like 34 KB, and that's like a huge code.
It's a lot.
It's a lot, yeah, and that's only comes up to be 34 KB. Now that's like 4.7 million files of this size, so it's a lot. And what they mentioned in the paper also, that normal engineer or normal software developer, they haven't seen this much number of code in their entire life. Not like, even if they haven't seen it in just one go. So that's why so that's why the sampling here is really important, and it's a huge thing for them also. So this is where it comes really handy. So the evaluation part is really interesting. So they have done like 163 handwritten Python code with unit tests. So the reason why they're doing it, because for evaluating normal text and images, it's a little different. But for evaluating code, like even in your general life, you have unit tests for that, and that's why they are the only reason. Like they tried a lot of other evaluation metrics, but they thought that unit test is like the best evaluation for any coding thing. So
what did they try? Can you comment on that?
So they tried something called glue. Yeah, so that, and I'll show you in the later also, but that it's not correlating. But there's one more aspect which is like code blue, which is by Microsoft, which surprisingly they did not try. And I'll show you, we tried it in our code. So so yeah, each problem included like a functional signature, a docstring, and a body, and a several unit tests. Which so in this paper they are taking like average of 7.7 tests per problem. So it is important for these tasks to be handwritten, since the model are trained on a large fraction of data, which already includes solution to problems from a variety of sources. So for example, there are more than 10 public repositories containing solutions to Codeforce's problems, which makes up to the recently proposed apps dataset. And that's why I think this is a really big deal, because they had to write everything manually. So talking about the apps dataset, so they use like 10,000 examples of it, and they use like 5,000 training and testing examples. And the two metrics which was used in the apps dataset itself is the strict accuracy and the one where your test case passes. So it means that if you have a unit test for a couple of problems, the number of times that the program actually passes all the test cases, that's called the strict accuracy. But a number of times the program actually passes the test cases, but it might fail like 1 or 2 times also. So that's not like non-strict accuracy, it's written. But in this Codex part, they're just taking consideration for the strict accuracy. And so coming to an environment where they're basically experimenting with this. So what they mention in the paper is that there are a lot of sensitive resources in GitHub. You have like names, you have like contacts and everything. So rather than doing it in like normal Docker, they are doing it in something called gvisor, which I don't know what exactly it is. So where they are, so they want it to be a secure place where they can experiment with everything, and so that the data set any data doesn't go into wrong hands. So that's the sandbox environment where they're trying to do. Even the human evaluation data set, if you want to try it, they will specifically tell you that you should be doing it in a sandbox environment. And unless and until you do not comment that code, you cannot use it normally. So you'll see an error. So that's why they used all whatever experiments that we are going to see in a sandbox environment, and just for the main reason that they wanted some security. So that's just what's happening. So to explain what repeated sampling is, which I mentioned before. So basically, if I have this text called practice, and I want to predict like what's going to come next. So I might have a lot of other predicted text as well, which is like he, great, influence in this case. But in this case, you might it might be a situation that the influence might be 0.8 and he here is 0.6. But going forward when you check it, it will be the actual accuracy the actual probability of that of the sequence will be 0.42, but here even after if it's 0.8, it might be reduced because you do not want that to be because the probability won't be matching that. So you will be taking the maximum probability which comes after like n number of sequences, and then you'll be taking that sequence itself. So here they have used that, and it's used for basically you checking like what comes in future, and that whatever sequence that you're taking is if it's correct or not. In our experiment, we are not using this repeated sampling. We are using something called causal modeling for this, language modeling for this, and I'll show you like how that happens. And that actually gives a lot more better accuracy than this repeated sampling. So in normal NLP also, you use like repeated sampling. There's a greedy sampling, and there's one more matrix which I think I'm forgetting. So the greedy and that one more matrix, they basically just go till this level, but only repeated sampling the only repeated sampling goes beyond the first level, and they go like till the end of the sequence. So coming to this, since we were talking about the unit test here, and this is like a very interesting thing which I found for evaluating the function correctness, is that they're using something called pass at k metric. So k is like the number of code samples that are generated per problems, and like if I say like problem is like n and k is like the code samples which are generated, then the total fraction of problem solved is reported. But what they mentioned is that this might be biased. This is actually biased only if n is less than c. So if like let's say for example, if you have if you're only generating one code sample for 10 problems, then it will give a wrong prediction, or even it will give a biased solution to you. So that's why for you to have an unbiased solution, you should have n which is greater than or equals to k. And that's what they are trying to prove here. I mean, they didn't give any, oh no, in the next slide they're trying to give. Yeah. So this is like where they're actually telling like this, the variance and the bias of two estimators for pass at k. While the top expression here, it might look correct because like the number of k as it increases, your correctness or like the sampling correctness that increases. But if your k is less than the sample, then as you can see here, it will be basically, it will give you a biased solution, or like not a correct solution every time. And here also, if you say the unbiased estimator might have a slightly higher variance initially, but allows you for a fair comparison across other number of sampling. So it might have a higher variance initially, but have a, as you go, as the number of sample increases, the correctness or this will increase. So this is what they're trying to explain by the bias.
So what is the rho again in the formula?
So in the formula, they are not telling like what's wrong. They're just saying that
No, the rho,
The symbol.
p value. Yeah, the symbol.
Where?
At the
1
top.
minus rho.
Oh, this one.
Yeah.
Oh, so this is basically also this is basically the number of, I think they haven't mentioned what that
Proportion.
rho is. The
Proportion
number
of
of
pass.
the number of pass values. So here, as you can see, the number of wrong values which are there. So 1 minus p of k.
Proportion of wrong, I guess.
Proportion of wrong predictions. I think they haven't mentioned exactly like what the rho here is doing.
Is it something like binomial distribution?
Yeah, it's kind of proportion,
It's kind of binomial.
but it's binomial times another. It becomes binomial. 1 minus binomial.
This is the only math equation which is there in the paper.
And p, supposedly p should be a fraction.
Yeah. So what they're trying to
P
say,
means rho 1. I mean, yeah. Rho should be a fraction.
so that's the probability of correct
Rho p.
I think so.
Yeah, it looks like p here, but it looks like rho on the
Yeah, I think it should be something like that.
Okay, anyways, I don't wanna stop you
Yeah.
with this, yes, sorry.
Okay. So coming to the result part of this, so there are a lot of so they also tested it on Tab9 dataset, which is basically a very popular, code generation library, which is present in Visual Studio. So as you can see here, the GPT-J passes pass at 1 is between 11.62 is between your Codex 8.5 here, and between this 8.5 and 300 million. So looking at so that makes sense because Codex is trained on Python code only, while GPT Neo and J are trained on your Pile dataset, which contains a Stack Overflow and your Python code as well. Now the problem with this is that since you're only working on Python here, you do not have the liberty to work with any other language. So the Codex might give you a good result when you're only working with Python, but it might give you a very good result if you're working with different languages. So considering that you are considering different languages for Codex as well. So that's where I think we guys were a little stuck, because we wanted to include different languages, but we couldn't because we didn't know how much data we had to include for different languages as well.
So you wanted to train it from scratch?
We tried to train it from scratch, but we couldn't because it's like so much data. So we had to fine tune it using the GPT-3 model, GPT Neo actually, at 2.7 billion. So results for the pass at K is that the GPT-3 that it definitely gives 0%, and that's given because it doesn't work on any code as such. But Codex S, so they have actually mentioned Codex S and D. So they are nothing but it's just fine tuned on competitive programming languages, and Codex D is just fine tuned on a smaller subset of that docstring. So as you can see here, for pass at 1, the Codex S is giving 37.7, but for 100 solution, it's giving a slightly higher, that's 44.5. And generating 100 solution, so what I couldn't figure out is what metrics they were actually checking for this thing, because it's essentially the same thing, but they are giving two different percentages for the same pass at 100 thing. So that's where I was confused, and I think I couldn't find any good resource also which could explain me that. So if you guys just look into it, you can tell me. And the scaling law is they're telling as the number of K increases, as the number of sample increases, as I think this is true for anything, as the number of sample increases, your accuracy should be increasing, and that's why they're saying that as the number of samples is increasing, your pass rate is going to increase a lot. But here, as you can see, the randomness, if you take any random value for the Codex, it will basically be decreased, but for the mean log probability, it's actually increasing. So that's what I want to show. So it's better to take a better metric than just randomly selecting the sequence which is going to come next. I think they also used a back translation for this, but that they mentioned there, but they didn't show the plot for this. So back translation is basically the generated code minus the expected code. Sorry, I think vice versa. So and how much accuracy you get, that's what you plot there. But they haven't done it here, which was really surprising to me while I did do it. And for the next is so they're checking the best temperature here. So the temperature is basically so it defines the randomness of the code generation. If it's close to 0, or even if it's 0, you'll only get a deterministic value, or it might happen that the code, even for one simple line, it might just repeat for the whole thing. But as soon as you increase the temperature or the randomness of it, and if you increase the sampling also, you'll be seeing a better result comparison to like what you have like with less temperature. So that's what they told us in the beginning also, and that's the result which they are plotting here. Yeah, so this is the blue score, which is a metric for for checking for evaluating a generated text to a reference text. So if you get a perfect match with the text, then you'll get a score of 1. And if you do not get it, then you'll get a score of 0. What surprises me here is that the blue score had no correlation with the Codex, that human evaluation metric, and that's where they were like that. I mean, this was supposed to work because this is like the main thing. Even if you're working with a natural language generation, the first thing you check is the blue score probability, and if that has no correlation with it, then what does it mean? And they still have that question open in the paper. But note that the distribution are not clearly separable. I mean, suggesting that the optimizing the blue score is not, as I said, is not equivalent to optimizing the functional correctness of the code. So that's what they're trying to tell you. The limitation of this codex is efficiency. I mean, you need to have a lot of samples in order to generate very simple code also. But as I mentioned in the paper also, the humans, they don't need to learn a lot of code. They just need to learn the logic, and then they will be coding it properly. But then they also talked about reliability in this. So if you have this Codex or like GitHub Copilot installed in your Visual Studio, you'll always be looking for that solution rather than coding by yourself, because you think that there's a helping hand for you, but it might be wrong, but then still you want it. So that's like a double-edged sword for them. As I told, the generated code might be syntactically incorrect, and might, for any function, it might also use like a lot of variables which are not even needed. So they showed an example in this paper, like even for multiplying two numbers, in the function like def multiply, they just give like ABCD, but the code, even in the docstring, they mentioned that you just have to multiply two numbers and give the output. But the codex was actually using all the variables which was given in the function, even when it was not even useful. So that's one limitation of codex. And they also saw that the performance drops when the length and the complexity of the docstring it increases. So even for a very well-defined docstring, like you tell like what needs to be done, codex doesn't perform it, and that's like it's really surprising why it doesn't do that. So the hazard of this is that the generated code looks correct, but that it's not correct, and it can also generate like toxic comments because it's trained on the publicly available GitHub repository, and it might be happening that if the data set has a toxic comment or something like that, then it will definitely be shown in here, so that they have no control over that part here. And insecure code is basically that even if so a lot of companies which doesn't include license.
That would also mean that any like Trojan horses might be in the.
A lot of things. Yeah, I mean that's why it's not. And there was an example where when you were so I think they were trying to code something with Hugging Face, and the API which you have, that's personal to use because you already paid for it. But that was I think that person, they might have done it in the private repository, but as soon as you were coding it, you can see the API for some other person in your docstring. So you can use the same API for your work. And that was that's where the insecure code comes up, because your private information is coming and it's going to some other person that you don't even know. Even your name will be name and phone number might be somewhere. If it's in the GitHub, anybody can access it. So they don't have any security code for that, I think.
Some people put their AWS keys to GitHub.
So
and that's an easy Bitcoin mining opportunity.
And also talking about the legal implication, as I was talking, so if an organization, if a small organization, they have like their whole code in GitHub, then anybody can access it. So it's like a very, and you can easily look into that code, because if you type like what define, if I have something in trends here, define trends code, and if it's already present in GitHub, then
Public.
What?
Publicly. though.
Yeah, if it's publicly,
Yeah.
then it will definitely try to match it with it.
So like as we guessed, right? It's a nice k-nearest neighbor searcher. It's like I mean kernel. Well, no, the retrieval, information retrieval is a very hard task. So that's what it's doing, basic information retrieval.
But then we came into the picture.
But how did you say 112 billion parameters and gigabytes? Can we translate gigabytes into billion parameters? Does it like actually just it can store it 3 times or something like that? What is it?
Yeah, that could be like the
But
objective function.
but that's the, I think the major thing that plays here is the filtering thing. So if you filter the repositories with like 1,000, even with like 10 stars, greater than 10 stars or something like that, then that might make a difference.
I have a question about the previous slide. You don't need to change back this syntactic correctness, but you can always check it pretty quick with the syntax corrector. Did they talk about of kind of a core running, like you generate something, but you quickly in polynomial time just say, okay, syntax is incorrect. Can they rerun the prediction to kind of to correct it on the fly or something?
So that, so they did talk about it in the future work. Basically, what they're trying here, they have not used anything like that. So in the future work, what they're trying to do, and what they have also done in the Codex API, like the web app, is that they are trying to implement a reinforcement learning. This, what do you say? For award function. So basically, if the syntax is correct, then it's okay. But if the syntax is not correct, then it will basically change the whole code and give you a new prediction. So, and that's how they're trying to like limit that and correctness.
Did they talk with the unit tests? Did they talk about like keeping the same unit tests but optimizing the size of the program
No,
or the speed of execution?
no. So that's not at all talked about.
Because it may still be
It's-
useful. I write unit tests and then I like give me the fastest program that produces that.
So
passes the-
here, when you look at pass at k metric, that basically looks into the time complexity and space complexity as well. So if I pass like, if I give like 100 samples and like I want that metric, so it will take the 100 samples and it will implement, like it will try to have a unit test for each of those samples, and then in the one sample or 1 or 2 samples which has like the best complexity, that will be given to you,
The one that passes
the one that passes.
But then I can use this to optimize the complexity.
Yes, then you
Like
you
I can change
Yes.
GPT-3 further by additional metric. Unit test is
you have
for
to train it
characters.
again.
Yeah, I forgot, we don't have AI, yeah, it should be on the fly, it should be learning every time it's doing something.
This sort of reminds me of an old Ken Thompson paper from security where it's called like Reflections on Trusting Trust. It's about Trojan horses in code. Like you can have like, you can do static analysis on source code. And then if you have like an infected compiler, the output will be infected even though you've done static analysis. So this kind of reminds me of that, like if somebody's like poisoning GitHub with static code or whatever, I mean, you would help do static analysis then, but your model would then learn how to code in a way that's poisoning whatever future code it makes.
It does make sense. I don't think they have any security related check.
Yeah, I'm sure. I mean, I'm sure that they didn't expect to get so good to be production ready. So it's kind of usually a late stage concern, but it's just an interesting thing that comes to mind.
So yeah, going forward, so this is where we come in. So we basically made a team of 6 people. So there was a Flax community competition which was held by Hugging Face, and so they were basically providing us free TPUs, and we need to make a really good model so that so that we can win. So I was a part of this GPT code Clippy, which is basically something which will be replicating what we have right now in GitHub Copilot. And along with this, I was also a part of DALI Mini, which is which basically it won the competition. So that was really great. Maybe in the next session I can present that. So we use open source, that's as I explained, we wanted to make an open source version of GitHub Copilot, and that was basically based on GPT-3. And we wanted to do the same thing which we are doing in the paper, but with a little twist. So what we did is that we have something called Skirt GitHub, which allows us to basically so Skirt GitHub, which actually allows it to have to the fine tuning very nicely. So we didn't take all the code in GitHub. We wanted just like a smaller subset of that. So we took repositories which have greater than 10 GitHub stars or greater than 2 commits, must have a license, should include a fork, and should be seasonable, less than the size of that 70,708 byte. And that was not a very random one, because we tried a lot of sizes, and when we take a huge size, it basically destroys the model, and it literally just destroys the whole thing. So that's why we just we limited the size of our
Why is that? Can you comment on that?
So we were actually not sure why that happened. I think since we were trying to since we were trying to also model a causal language model, I think that model itself, it was not able to take the whole
All
data
sequences.
set, all the
And you
sequences.
didn't chop them.
So no, we did everything, but I don't know, it still didn't work. There's still a to-do list to check why it did not work. It's not a perfect thing, but we still. So yeah, so we compile this GitHub repositories, which are also there in the pipe, and then after that we filtered all the duplicate files, and that's a way. So there's a way of called deduplication of files. So we use that metric. So basically what it will be doing is not just the file name, but also if the functionality of that code is same, then it will not take it. So that's something that we worked on, and that includes the variable that actually includes variables and the functionality as well. So in order for us to do that, basically what we did is we used the Hugging Face transformer library, and since we got the Flax API for us to train in TPU, we use that as well, and we modified the batch size and the learning rate, which we took the suggestion from the Ethereum AI guys, and they told us that they helped us a lot, so that made it easier for us to work on. And so after fine tuning, so it allowed us to converge faster than the training from scratch, and therefore all the version of our model are all fine-tuned. That's the reason we didn't go from scratch, because we already have GitHub. Even the Codex people, they didn't do it from scratch, so they also fine-tuned to the GPT-3 model and then did it. So we tried something called as I mentioned, instead of the repeating sampling, we used causal language modeling. So what it did is that in the example as I showed, this one, so in this example, instead of checking for probability at each step, we are actually going to the last of that sequence. How causal modeling does is that it actually created a graph, and that graph is basically it will be telling me that in the end, the leaf part, it will be telling me if that accuracy is good or not. So we are not seeing so for each and every level, we don't have to go and check the probability. We can just look at the probability at the leaf nodes. So that's where we thought that we can actually use that. We can use that concept to make it faster than what we have right now, and that actually worked pretty well. So if you guys want to try this causal language modeling by yourself, there's a link. I'll attach a link, but this is what we did for for learning as well. So this is pre-training a transformer model on TPU with Flax syntax, and they have each and everything, and you can also try to code your own language model as well using this. So this is the evaluation which we did. It's pretty bad compared to what we have in Codex. But as you can see here, we took like GPT Neo, like that's the main model which we took, and the pass at 10 is like that's not even the best one, but it's still pretty good because we are at a place where we can actually if we take like more samples, then we can actually it can be better. So we haven't tested. We did test it for 1,000 samples also, but I don't think we took that into consideration for the table.
How well did the other people score?
Sorry.
How well did the other people in the?
Show us leaderboard.
Oh,
So we like.
so yeah, I'll show you the other. So one person, his name is Nate. He is a PhD candidate in Washington University, I think, and his main research is this one. So as you can see, this is like a demo of our GPT code, GitHub Copilot, where just a minute. So as if I'm going for loop for 1 to 10, you can see that there's a line there. I'm not able to pause it. There's a line which comes like extra line of print. That's where it basically it's wrong. So we don't need that extra line of code, but otherwise it works fine. But then it's just a very simple code. If you try to do it for a very complex one, then it will definitely fail. So
Oh, you remove that print and then
yeah,
you
we remove
execute
that
it.
print and then we run it. Yeah, but initially if you try to predict it, then that print will also come, like the second print line, which is not needed. And for you to check it, this is the GitHub repository. But I'll show after this because I have the window of presenter view, so can't show it right now.
So you did it after Codex paper or before?
No,
Codex?
so we did it after Codex paper.
So it was kind of inspired by,
Yeah.
can you make the same that they did?
Yes. So I mean, we had like only 1 month to do this, so that in 1 month I think that's still okay. So my opinion on this paper is that the pile dataset only uses like 5 GB of. It has only like 5 GB of data, but it performs really well even in that dataset because I mean, I think it includes like Stack Overflow and Python files as well. The filtering plays a huge role in this, and as I mean, even if you take like unfiltered or like the raw data set, you will find that the accuracy of your predicting the code that goes significantly down. So your filtering definitely makes a lot of sense. And also, so what we tried here is that we didn't try only for Python, we also tried for different languages. So we tried to make something like universal abstract tree, which so for example, if I have JavaScript and C#, the syntax might be similar, like it's not that similar, but it might be similar, but we wanted something to do like if we have like the docstring or like the comments, then it should be able to map the syntax for each and every language, be it Python or JavaScript or anything else. So that's where that's where we wanted to work on, and so we created something called universal abstract tree, which is not implemented in Codex. And a very surprising thing which I find in this paper is that I mean GitHub Copilot is basically owned by Microsoft, but no one from Microsoft was mentioned in this paper. I don't know why. That's one thing, and also like they did not consider code blue metric, which is super weird because code blue matrix that it actually captures the semantics and syntax of the program. If they would have done it, I think it would be more clear for us like what's happening in the like within the code itself. So that's my opinion. Any questions?
Is there a ranking for the thing that you?
Oh yeah.
Because like the numbers seem pretty low compared to the original paper, which makes sense. But I wonder with the other teams, like how they relate to the other team. Because like compared to the paper, it's obviously like they use like.
Oh no, so they did not. Oh no. So this is the in the competition, like we can choose any individual projects. So
Right.
we were the only one who are working on this.
No, right. That makes sense. But like how did other people perform in terms of their tasks?
Oh, in their task. Yeah, I think I might have something like that.
But
No.
their task wasn't Codex, so we can't compare.
Yeah, they.
You're only comparing Codex with what Mrinal has done in his team.
Oh, so the competition was about Codex, right?
No, the competition was about just using the Flags API.
Oh, okay.
Yeah, so
Okay.
they did like different projects, like different projects like Dalimini and all that, but we were the only one who worked on this Codex thing.
Okay.
So that we don't have like any comparison with somebody that.
Oh, so it was very, the way they chose the winner.
So they chose the winner by how accurate your model is, and like how good the public responds to it. So we tried, that's why we tried to make that extension, Visual Studio extension, and we tried to give it to all the community people, and then they tried it. So.
Okay.
Yeah. Any other question?
Yeah, it's open to questions now if our.
Where do you think this is going?
Oh, we are still working on it actually. So every weekend we sit, all of us we sit together and we do like pair programming. I mean, even like tomorrow and the after tomorrow also we will be sitting together and we'll be working on it. So,
Right, but in general, the field like, of code.
so yeah, we just want to make a like open source of GitHub Copilot. I think that's what we want. So we wanted like a community service like this, so that I mean we don't know right now that where like what does Copilot actually do, and I mean since it's hidden for obvious reason, but what we wanted to do is we wanted to make something better than Copilot, and since Copilot cannot really perform well on a lot of like as I showed the limitations, it has like the no secure no security or something like that. That's why we wanted to come in and we wanted to make something much better.
And so do you think this is the future, using like transformers and stuff, or do you think symbolic computing, which I think they're working on at like in Carnegie Mellon at MIT and I think Microsoft, they're doing a lot of like, they're actually straying away from transformers because of kind of the way you kind of frame it is like it's a KNS basically, it's a statistical model.
It's nice.
Right. And but they're trying to do like really like object, you know what I'm saying? Like they don't look at it as like, oh, we're just gonna learn on this huge data set and then predict, but they're looking at like, can we create trees of like, it's more like a compiler
Oh, okay.
learning sort of, where you're more constrained.
Well, I think no, yeah, I mean I don't know about this. So
But do you, okay, so maybe the better question is, do you think this is actually gonna work in the future? As in like with
this thing or like
not specifically your project, I mean, I get that it's like probably gonna have like, it's gonna work to like extend where it's
Yeah.
very usable.
so
But my question is like, is it actually like gonna work, understand code?
so what I could understand from your question is that if a normal, let's say a non-coder person, if he can code like properly given a specific set of problem statement.
I think more like, do you think it will actually understand code? Because code, like the thing about code is that it's actually not like language, it's very structured. Like
Yeah,
human language is sort of structured, but it's a little more like, you know what I'm saying? Like
yeah.
computers have like trees of how they execute things.
So yeah, I think so. I mean, this is a very evolving area as of now as well, because I mean this is just like the starting point, and for even I don't know, this might be very useful for the users, but I'm not really sure like how they will be able to implement like a very perfect. I don't know, like GitHub Copilot, something like that.
Right, because I can understand that this goes towards like being usable,
Mhm.
right? But I wonder like if we actually get sort of like the best thing we have right now for like creating code that works as fast as possible, for example, is just compilers, which are
Right.
super heuristic.
No, humans are still better, but they're slow.
That depends. I mean, you can't write a good what's it called again? The lowest level code.
Assembly, humans are better at writing assembly,
No,
but
that's not
they're slow.
Not than the C++ compiler. It's actually provable that it's like one of the most optimal. Yeah, okay, if you take in a limited amount of time, but that's like.
Well, take any small problem that a human can solve, humans will solve it better still than a compiler.
Not always.
Always.
No, that's not true.
Yeah, that's true.
No, it's actually Bjorn Stormstruck, the designer of C++, said that like most things that were implemented in assembly, they actually improved after they created the new C and C++ compilers because it wasn't implemented efficiently. Because the compiler found better heuristics, or better ways of compiling code than.
I think if you sit down and think about it, you.
Yeah, but that's like,
Yeah, it's
That's a
inefficient,
good
but we
question.
can find better solutions still.
no, I believe that. My point is more like, can we make it even better than compilers? I'm talking about like code based. I know that humans are like, that's,
Yeah, well, that's by intuition, so, but what is happening, I disagree with code being structured. The code is locally structured in a sense, but the same problem can be solved in infinite number of ways.
right, but the
Because
way,
globally it's restructured, it's same compiler, and the code is just a function.
no,
from
what a
inputs
computer
to-
can do is very structured. There's only a limited amount of possibilities that you can give to a computer at a certain time, which is not true for humans, because humans are like inherently not sort of like binary.
You would think so, but like I don't see much difference between language and programming languages in a large scale when you look at like larger.
No, but we design programming languages for humans right now, but like a model could learn like a way more efficient way of communicating with the computer. Like it doesn't.
Oh,
have to be-
yeah, so it should be in assembly, like, or in
For
binary.
example, yeah,
It
I'm
should just
talking about,
produce the
like,
binary
could we
code.
create something that like, if you give it a problem, is like, oh yeah, this is like the most efficient way to do it. It doesn't have to be in Python. I mean,
Yeah,
I understand that this is like a, you know, a usability thing where you can predict like what you're gonna write. But I'm wondering in the future whether it can improve. I mean, that's like the future of like improving itself, right? If you're like, hey, I want a neural network, doesn't have to be written in Python. It could just be anything, as long as it works.
You are saying that the code the computer or the model should generate is understandable only to the machine.
Well, it should do what you want it to
Yeah.
do, but it doesn't have to be, you know, the code the code we generate with Python is not understandable to me either, because at some point it's assembly. And then basically it's like, yeah, I don't know, what is happening?
Well, assembly we can understand, but I mean, yeah, you.
I mean, if you
binary.
look at a neural network in assembly, I'm pretty sure it's gonna be, it's gonna take you some time to understand what is happening.
So I do want to give a taste of the Codex API which they have mentioned here. I think I just checked like, okay, let's try this. Yeah, so so this is where all the parameters that we've talked about this here. So this is the presence penalty which which I talked about. They're using the reinforcement learning parameters here. So if I increase it and like as it's written there, so they penalize the new token based on whether they appear in the text so far. So that's where they're trying to use the syntax or the correct syntax of that. So even if I like try to just say submit it, like I don't know what this code is doing, so it will just give me like what actually that is. But this is like this can be done by a normal GPT-3 as well. What I wanted to share is this, like given a natural language, like how you are trying, you want to code it in Python and then you just submit it, and this is like how. So now this will show two things. First is that these names, they might be like from where this code is actually taking the names. It might be something private, you don't know, and it's it's definitely not random. You definitely might know some John Smith or John Doe or something like that. So this is where the security thing comes up. But as soon as I so this is like pass at k parameter here. So if I take a best of 9 and let's say I try to do something else, let's say implement, and I don't give it anything else. Like I don't specify which framework I want it to be presented. So it will take some time because it's definitely taking all the best of 9 code that will give me, and as soon as that happens, it will. So here it's taking the torch framework, and and it will just give me like the whole code. So here, as you can see, it's like it's limited because I have put the response length as 300. If I increase it, it will give me the whole like the number of tokens which is specified in the response length. So yeah, and okay,
is that code?
Yeah, this is the repository which I was talking about.
Your repository.
Yeah, the GPT code. So yeah, to look through it.
Yeah, pretty good. That's a nice talk. Thank you so much. Yeah, that's very interesting. Yeah. Stopping the record.